Well, good afternoon, it's Charlie, ZL2CTM. Well, I just have had a chance last night and this morning to design up and build a driver amplifier, which seems to be going reasonably well. So I just want to do a video looking at that. So this amplifier here is going to sit between the antenna RF amplifier, which is playing two purposes. On receive, it's amplifying just by 10 dB the receive RF straight out of the antenna, and then on transmit it's a pre-driver, so to speak, providing just a little bit of 10 dB gain before going into the driver stage here, and then eventually into the power amplifier. So we'll look at the design in a sec, but and then we'll come back and we'll flash up the oscilloscope and put some signals in and have a look. So let me just zoom out here. Another purpose, what I wanted to do with this design is hopefully come up with an amplifier I could use in other circuits. So in terms of broadly what I was aiming for, two things. In terms of this particular build, the output of the RF antenna amplifier, the one that's doing two purposes, is around 2 volts peak to peak. So again, 0.2 volts peak to peak. It's sort of normal to loud sort of voice volume there. I need to crank that up to about 10 volts peak to peak in order to drive the push-pull amplifier. So it gives me 20 log what I need versus what's going in, gives me around 34 dB. For this particular amplifier, I'm going to have a, even though I've written down 34 dB there, I'm actually going to aim for around 40 dB. So that's going to be my overall gain for this amplifier here. Ideally, it needs to be at least 200 millivolts, so again 250 milliwatts output into a 50 ohm load, and again that equates to that 10 volts peak to peak that I use, or that I need for this particular radio. But I think that in terms of usefulness, that'll be quite useful for other builds, and by all accounts it's actually closer to half a watt, which is good. I want it to be broadband, so I want it to be useful across the HF spectrum. It's not dead flat, and it's actually in keeping with another driver type amplifier that's in the EMRFDs, so I'm quite happy with that. I'm going to use two N3053s as opposed to, say, the 2219A. This particular device here has a much greater power dissipation than, say, the 2219. And as you'll see, for the first stage here, it's going to be a two-stage amplifier. I want to have going through the first stage 50 milliamps, and then I want to have 100 milliamps going through the second stage. So by using the 2N3053, I've got a much greater, well, in fact I can dissipate the energy that's being lost across that due to inefficiencies of the class of the amplifier. For the first stage here, I'm going to aim to have a collector impedance of 200 ohms. And then the second stage will be the RFC feeding into a 50 ohm load here. My initial design was just thinking about the idea of having feedback on both circuits. I think that's an overkill, and as you'll see later on with the LTspice that was, but it was more just sort of playing around and having a bit of a think for a start, would that be a good idea or not. So I actually designed to have those in, and then as you'll see with the LTspice, I modified them out. So for 50 milliamps on the first stage, in fact also with the second stage, beta DC off the spec sheet, so we use a geometric mean, square root the minimum value in the spec sheet times the maximum value, comes out at 111, and I've used that beta DC for both the first and the second stage. So I won't sort of go through the calculations in any depth, that's what we've seen before, but sort of just to go through them. Again, setting for both the amplifiers the emitter voltage to be around 1/10 of VCC. Another thing too, I'm going to have the VCC for this amplifier sitting at 13.8 volts as opposed to, say, 19.5 from that laptop power supply. So sort of makes it a bit more sort of generic for use other than, or for other radios other than this particular radio. So 1/10 of VCC at the emitter divided by that 50 milliamps gives me my 27 ohms for the emitter resistor. Again, the voltage at the base is going to be 0.7 above that at this point here, and I want to have 10 times the base current going through R2. Apologies for not labeling here, R1 and R2. So 1.38 plus 0.7 divided by 10 times our base current. So we'll have our collector current is essentially equal to our emitter current. So we can just take that 50 milli divided by 111, gives us 461, comes out at 470. Same scenario for the R1 value up here. I am going to take into consideration the voltage drop across that 10 ohm resistor, which we see here. So 50 milliamps times that 10 ohms will give me some voltage drop across that. So therefore 13.8 minus that gives me the voltage at that point, minus the voltage at that point divided by the current through it, which is going to be 11 times, because it's 10 here, plus an additional base current. Comes out at 2264, so we'll use a standard value of 2.2k. As was seen in the EMRFD, I'm going to determine, for the sake of, apologies there, for the sake of experimentation, the degen. So in this particular case, there's a rule of thumb, I guess, that's sort of laid out in EMRFD, that RF, our feedback resistor there, times RE, where RE equals little re plus RDgen, which is the overall RE here. Now this is going to be quite small in comparison with our emitter resistor, so I'm going to ignore that. So it's going to be little re plus our RDgen. And noting also that gain is approximately equal to 10 log RL divided by RE, the same RE as we just seen here. So working backwards, we want to work out what RE is. So, and we know RL equals 200 ohms, so therefore we can rearrange our formula here, noting that we wanted to ideally have a 20 dB gain out of this one. So we can say 20 dB equals 10 log 200 divided by RE, our unknown. We can rearrange the formula, solve for RE equals 2. And we know that little re is 26 divided by our emitter current in milliamps. So we can say 26 divided by 50 equals 0.52. Therefore our RDgen equals big RE minus little re comes out at 1.48. So we'll use a standard value of 1.2. RF, that's our feedback between the collector and the base. From that formula which we saw before, we can then now solve for RF. So RF will equal our source resistance of 50 ohms times our collector resistance will be presenting to the collector of 200 ohms divided by 2. So we're bringing that 2 to the other side of the equation. Solving that comes out at 5,000. So we'll use a standard value of 5.1 k ohms. Right, for stage 2, much the same. So let me just bring back the first page. This stage here, nothing special there, apart from the RFC and no bypassing of our emitter resistor. I won't go through these ones, but again, in this particular case now, our quiescent current is going to be 100 milliamps to give us a little bit more power output from this, as opposed to a purely a small signal amplifier. We want to get a little bit more gain out of it. Beta DC, as we said, is 111, and same logic again. Our big RE, our emitter resistor, is going to come out at 12 ohms, so we'll use a 12 ohm resistor there. R2, the lower resistor, in our voltage divider biasing, exactly the same as we've seen before, apart from just substituting in 100 milliamps for our collector current, equals 230, so we'll use 220. R1, in this particular case we don't have a 10 ohm resistor, so we can just take straight our VCC minus the voltage at the base, divided by 11 times the base current, so we'll use a 1.2k. And then again, exactly what we just saw for stage 1, solving for big RE, and then solving for RF. So I won't belabor the points there. Note there's no degenerative resistor on the second stage, so it'll be big RE we'll be using for that particular case there. What else do I want to say about that? And our degenerative resistor, so that's RF, and then our degenerative resistor, 20 dB again for the second stage, 10 log RL, which is our load resistor. In this case it's going to be 50 ohms, I think that's about right. Let me know if I'm off there, but like I say, the actual results worked out to be pretty well spot on. Divided by our big RE, again solving for big RE equals 0.5. We've got our little RE there, 26 divided by 100 equals 0.26, and therefore we can come out with our degenerative resistor of 0.24. Noting I actually didn't actually use that, but I just did it through the calculations anyway. So LTspice, and I'll show that in a sec. After some experimenting with LTspice, I elected to only have the feedback, the negative feedback on the first stage, and that's what I settled on in the end. So you'll note there's now no longer our RF going back from the collector back for the base, and certainly on the second stage again, no feedback between the collector and the base. So all the negative feedback is being applied here on the first stage. And like I say, I'll have a look at LTspice. So for 80 meters, LTspice was saying it was 36 dB, and that's exactly what I'm seeing in the real world tests. 40 meters, 32 dB, and 20 meters, 26 dB. Anything else to mention on the main circuit is the first stage is a bifilar wound on a FT37-43, 2 turns, and configured in such a way that the 50 ohms here has been transformed back to 200 ohms on the collector circuit. And that was using number 28 just to squeeze it all in. And then our RFC on the second stage was 10 turns, again on FT37-43, but this time a slightly heavier gauge, number 24, just to account for the greater current flowing through that particular device. So just switching across to LTspice, hopefully that'll come through there. Apologies for coming off the screen. So as you can see there, that is the circuit. I hope that's visible. Let me just blow that up and then we can go back and have a look. So that's exactly the circuit we had there. In terms of simulations, we've got two options we're looking at. We've got the frequency plot or the bow plot, and then also in the time domain. I'll just look at the frequency domain at this stage of the game, but again that's exactly what we had. And the beauty of LTspice is, you can actually then play around with, like we see down here, with that degenerative resistor to get the overall performance we want. So just simulating that, and then going on to let's make sure it's on the output, and we can see there that we've got an initial gain there of between 38 and 40 dB, so let's say 39 dB, rolling off to at their highest frequency, which is 30 megahertz. We're rolling off to something like 20 dB. So for the bands of interest, like I say, 80 meters, so 3.5 megs is sitting around here, and as I said, that was 36 dB, and then 7 megs for our 40 meter band, sitting on around 32 dB, and then up on 14 megahertz for 20 meters, sitting there on around 26 dB gain. So and like I say, in the time domain, it was nice and linear, which was good, which is fine. Perfect. So moving through to the setup here. So for testing, let's see if we can get this in. The input here is coming from our SIGGEN, and we'll vary the frequency and have a look. At the moment it's on 3, it's just playing around with 80 meters, but like I say, we'll look at that in a second. I'll go back up. Oh no, we'll leave it there. And scope is sitting on the output. At this stage of the game, the output is just a small 50 ohm dummy load, so just coming straight off the output. I left some space on either side, and I'll zoom up in a sec to see how the board was made for some input and output transformers. At this stage of the game, I've just left room for that, but haven't designed anything in terms of interfacing with our power amp. So if we were to just move up to there, let's see if we can zoom up a little bit. So if we were to key, so we're now keying that at 3.5 megahertz, and if we were to do the maths on that, that is on times 1, it's on 5 volts per division, so 5, 10, 10 was it 12.5. So do the maths on that, that comes out pretty well spot on for a 0.15 volts peak to peak input. That comes out to be pretty well spot on 32 dB, 36 odd dB I should say, sorry, which is very much in line with what LTspice was suggesting we were going to get. So pretty happy with that. So we're just bringing the frequency back up to the 7 megs. So we're now in the 40 meter band. Our gain there. Again, so still getting a reasonable amount of voltage there, so still on the same volts per division, so 5 volts per division, so 5, 10, haven't actually dropped too much at all. And again, like I say, that's still sitting around 32 odd dB of gain. If we now bring that up to 14 megahertz, so let me just bring it up to 14, so that's 14.1 megs. And if we were to do the maths on that, I've only got a 30 meg scope here. That is coming out around 26 dB, like I say, so that's still pretty good. So that's on 1 volt per division. So 1, 2, 3, 3.8 volts for 0.2 volts going in. So I'm pretty happy with that. I think at this stage of the game I'm not going to try and do anything more to coax any more gain out of that. I don't want to risk instabilities and the like, but overall that's giving me the amplification I'm after for the amplifier. So if we just go back down to 7 megs, which is there, 7.1 megs. And just back up to here. So if my maths is correct, we've got 5, 10, or 1, 2, we've got 1, 2, 2.8 divisions. Yeah, 2.8 divisions. So 2.8 divisions times 5 volts per division gives me 14 volts. And I've got 0.2 volts going in, so 0.2 divide, and then I can go log 20 times, gives me 36.9 dB gain. So I'm a little bit lower than the 40 dB for a start, but honestly that's not too far off. And if we looked at, what did we just say there, 2.8 divisions, so 2.8 equals 5 times is 14 volts peak to peak. Divide that by 2, multiply it by 0.7071, gives me the RMS, square that, divided by 50, gives me 0.489, so just sitting under half a watt of power going into that little dummy load there. So I think that's, unless I did my maths incorrectly, that should be more than enough, hopefully, to, once I've got the matching sorted out, to drive our power amplifier. I guess the only thing else I wanted to talk about is, with a reasonable amount of gain there, what I wanted to try and do was minimize the possibility of instabilities. And I do acknowledge that this strip board here is not the best board in the world to use for RF circuits. I do hang down reasonably low with the 7 meg, so it's not too bad. But what I have done, and you can probably see it in the picture there, there's a number of places where I've used the drill to cut the tracks around the place, and the whole logic there was to, if I was to zoom up on that and come out a bit, I've cut tracks, say, between where the collector is, so there'll be a cut track there to minimise the high voltages here feeding their way back into the base. Again here, I would cut it here to stop any voltages appearing across our emitter resistor feeding into our base. So that's what's you'll see around the place with all these various cut tracks around the place to try and minimise that. Trying to minimise RF getting onto the VCC line, which is at the bottom of the picture here, and just trying to stop RF from getting back into the start of the amplifier by cutting tracks around the place. And I found, and this amplifier is certainly no different, that works particularly well. Now this is still keyed at the moment, so that's been running now for, I'm not quite sure how long I've been rabbiting on for, but they're still, this one's warm, this one's warm, but certainly I can squeeze it like mad and I'm not burning myself. So I think that's not too bad at all. Worst case, of course, single sideband would be a lot less than that. So I think that's probably all I'll talk about from here. So I'm pretty happy with that. I'm pretty sure the maths was right, and I think it was an interesting exercise, and I've said it before, and I'll certainly say it again, to work out a circuit. And I've certainly read this in textbooks that the mathematics and to a certain extent the simulation will get you in the ballpark, build it up, and then fine tune it. Yeah, full stop. I actually found with this particular amplifier that the current configuration is exactly as per the LTspice, which was based heavily on the maths. So it actually worked out to be quite good. And like I say, across the frequency band, I'm not seeing any instabilities at this stage of the game. Admittedly, it's got a nice clean resistor on the load, but at this stage of the game, it doesn't appear to be running away or any kind of instability. So that's pretty good. Rightio, well, I'm going to say 73's there, and I will now just have a quiet think about what may need to be introduced here by way of an input transformer. That'll be based on an FT37-43, and then on the output, what's needed to interface the driver with the input to this device here, our power amplifier. Yeah, so I'm not quite sure what's the best way of doing that. I'm kind of thinking potentially having to work out what the input impedance is for this device, and then work out what a transformer ratio would need to transform that back to 50 ohms. Or I might just feed this straight in and just see how things play out. So I'm not quite sure about how best to do that one, but we'll have a bit of a think. And same with the input. The other amplifier was designed, the amplifier, or the pre-driver so to speak, is expecting to see 50 ohms on the output, and this driver here is expecting to see 50 ohms. So we might just get away with just having those plugged straight in. But anyway, enough there. I'm starting to ramble, so I'm going to sign off. But like I say, more than happy with that, and we will continue playing around. Okay, cheers all.